10 minutes are up. So we are back with the lectures. We check that everything is working again. So the stream is up. So this time it also can hear me very well. For those obviously that now sit at home and study from home, no problem. Let me see. Yes. So apart, together, and cancel. So with apart, together, and cancel, we handle fractions, right? And you know fractions already. X divided by y. Right? And sometimes you have x divided by y plus a divided by b, and you want to find a common expression. So together finds a common divisor. Do you know what's the divisor? So when you have a fraction, you have like a line and then b on the bottom, right? Everything on the bottom is the divisor. Okay. So how do we do this? Let's work with an example. So we have here a very simple expression, 1 divided by x plus 1 divided by y. So if you want to find the common divisor, what do you do? Well, the left term you multiply with the divisor from the right, and the right term you multiply with the divisor from the left. So what you will get is x times 1 divided by y plus y times 1 divided by x. How do we tell Python to do the same thing? Well, we take the expression and say, hey, do together. And then Python does exactly that. So far, so good. How about, does it work with 3? That's a good question. I was like, how do we do a common divisor of 3? Well, a little bit more work. Works the same, however. Then Python should be able to do this as well. Let's wait and see. Magic. Okay, so it works, right? And even more complicated expressions you will be able to handle like that. So far, so good? So together. So cancel, cross out shared fraction in divisor and dividend. So sometimes you can cancel out, like factor out a factor of x in the divisor and the dividend. So when you know what's a divisor, I think you can guess now what's here referred to the dividend. I think that's the thing on top. So in a divided by b, a should be the dividend and b should be the divisor. Okay, so let's see. So we have here an expression x times our expression. Our expression was 1 divided by y plus 1 divided by x plus 1 divided by. So what we could do here actually is expand, right? Doesn't expand. So can we do cancel? Does it still work? Interesting, no? So expand did not do us any good. Do you see that? So before and after expand, yeah, it wasn't very helpful. Did I do it correct? Actually, I probably didn't. Bucket. Always be careful. Aha. So what's the difference? So we need to be careful what we actually ask Python to do. In this part, I first do the expand on expression and then I multiply with x, right? But I actually want to have x multiply with my expression and then everything being expanded. And then it looks okay. Okay, but in cancel, it works a little bit differently. In cancel, we basically have a combination of together and then remove the common terms that can be removed. So far, so good. How do I make sure that everything works? Well, I go on top here. I ask for together on the combined expression. And then hopefully everything will be the same. Looks identical, yes? What is easier to implement? The top or the bottom? The bottom, right? It's also easier to read. Okay, so you can work with cancel and has a benefit. A part, I think, is basically the opposite of together. Let's see. We have a nice example here on top already. Let's work with a part on that. Wait, doesn't work. Multivariant fraction, partial fraction decomposition, yeah. Compute partial fraction decomposition of a rational function. Okay, so didn't work because it's multivariant, meaning we have too many variables actually. Just let me, not found. Okay. So we go here again. We go to our example. We actually can look a bit closer into our example, just see what it is written out, and then compare to the apart result. So this is apart. Before we just have 1 over x squared plus 3x plus 2, which looks like this. But we basically can take terms right apart that come through in handy at some times. So I'm still a little bit stumbled why apart did not work here. Because yes, still doesn't do it. Not implemented. Multivariant partial fraction decomposition. Yes. Keep note, it doesn't work with multivariant expression. Right, so here, keep an eye out. This is important. Doesn't work with multivariant expression, which I forgot. What is a multivariant expression? It has more than one variable. So if you just have numbers and x, or just numbers and y, apart works. But when you start mixing x and y, then apart has an issue, and it will tell you, no, thank you. Nobody told me how to do it. So far, so good. Questions? No, right? So in the next part, we look into how to handle numerical expressions. So we have already seen some SymPy functions can work with numbers. But there's more to it. For example, we have a very, very complicated formula, and at the end, we want to have a result in form of what is the number actually behind this. And when the algorithm tells us, oh, this is 1 times 3 pi 4 half, right? Then it's like, okay, this is very good, but what is the number? Yeah, pi is a symbol that carries the meaning of a number, but we want the number. Right, and the other part is how do we actually then take our symbolic expressions and combine them into NumPy. Okay, so here is an example. Right, so 4 divided by pi divided by the Euler number. What's the value behind this expression? I don't know. What can I do? Well, I can use SymPy's n method that provides me a numerical representation. Right, so a numerical value. So again, I have 4 pi divided by Euler number. It's different from above. But when I take this and I plug it into SymPy n, I get the value behind it, in principle. So here's the symbolic value. And here's the numerical value. Very easy. Use SymPy n to give numbers where it can be given. Okay. Now I change this to the example up with divided by, just to be consistent. Okay, so the NumPy communication here I didn't put in, so it will come later, but it will be there. Okay, now calculus. Oh yeah, that is the fun part, right? Do you remember first year university calculus and algebra? So calculus, what is it? It's the study of continuous change. So continuous change is basically all the derivatives, right? Well, and the inverse of that. That is the integral. So far, so good. Everybody seems very, very focused. Shall we just continue or yes? Okay, we continue. Very good. So in SymPy, we work with expressions. We know how to handle equations. And when we have a very simple equation, we know that fun bit of it is to take the derivative. Like, oh, where is the minimum of x squared? How do we get there? We look for the derivative and where that derivative is 0. SymPy can help us to get derivatives. Okay, how do we do this? There's a function called SymPy which takes a function f and a symbol to which respect the derivative should be taken. Let's look into next up. We have here SymPy symbol f and SymPy symbol x. So we have f and we take the derivative with respect to x. What should we get? 0. Is this correct or wrong? Well, it's correct because here f is just a symbol. We have never said that f is a function of x, right? So what happened? Doing it right this time, telling Python f is actually a function. So when we have symbols, right, they're supposed to be independent of each other. If you have one symbol a and you take the derivative of that symbol or variable with respect to x, well, then if they don't depend on each other, that is 0. So far, so good. Okay, so how do we define a function? Well, we use SimPy function. We say how we want to represent that function here with an f, and what type of arguments it takes, x. So when we look into f now, we actually see f is a function of x. So far, so good. Now, when we have f defined as a function, we can say, hey, give me the derivative of f with respect to x. And Python will be like, what is f? Oh, you don't know, then I can just tell you, well, the derivative of f with respect to x is the derivative with respect of f with respect to x. As correct as possible at this stage. So far, so good. Okay, let's try something out again. So when I in b here, what do I get? Zero, right? Because b is just a symbol. That does not depend on x. How about b times x squared? What do I get? 2bx, right? Because the function here is bx squared, derivative of bx squared with respect to x. B is a constant, goes in front, and then the derivative of x squared is just 2x. Okay, so I can provide an arbitrary number of arguments, or at least more than one, more than two arguments with in this function. So any additional argument with an extra derivative. So when my arguments are f, x, and x, I take the derivative of f with respect to x, and then I do it one more time. So that is that d squared over dx with, of f. I can change it to b, right? But be careful, f does not depend on b. So this should be 0. Python is clever enough. So what we could do, we go above here in the function definition, and now we say f is a function of x and b. And you see I changed the function definition. I have f, and f depends on x and b. Now you see f depends on x and b, and derivative is now d squared divided by dx db of f. So far, so good. So multivariant calculations are no problem. So the next section actually introduces this a little bit more. Here's an example with f, x, and y. It is 0 because f doesn't depend on y. I fix this because I can just define a function that depends on x and y, and then I can take the derivative, which is non-zero. And as you see here in this example, I can add many different variables with which I want to take the derivative. So 14 students here, not bad. Okay. To make it a little bit easier, there's another notation possible. So x3, y3 would be that you take 3 times the derivative with respect to x and 3 times with respect to y. You can also put 30 here. Then it would be 30 times the derivative with respect to y. So far, so good, right? So, and now you're like, that's very promising, but does it know all the derivative rules? What derivative rules do you know? Product rule, chain rule, right? And there are a few others. So let's check if Python does the chain rule correct. That's fun, right? On a Monday morning. Okay, so we have here a function of g that depends on x, and we have a function h that depends on g. Right? So the inner function is g of x, and the outer function is h of g. Let's check if we did this correct. Looks good, right? So now when we take the derivative of h with respect to x, can we do that? Right? And I assume you remember the chain rule, right? Okay, so what we do is to take the derivative of the inner function with respect to x, and we take the derivative with respect to derivative of the outer function with respect to inner function, right? So we replace this one with n, and this one here is normally then also n, right? And you take that derivative. So far, so good. How about we test this a little bit more, right? Just for fun. So when we have here x is now a function that depends on t. And t is a symbol. Still correct. What is this? Very nested now, right? So, but the thing is, when we execute now the derivative with respect to x, we shouldn't see much of a change, right? It's still the same, but now with respect to t, it's a little bit more work. So it's a chain rule applied to the chain rule again. So I see 1, 2, 3 parts to it. So far, so good. And that should be all right. So some practical example, a little bit less abstract, right? So did you ever take the derivative of sine x squared? No, right? Why would you? But let's do it. So we have here a symbol x, we have sine of x squared, and then we differentiate the function with respect to x. How about first we actually can look into x, sorry, into h, and then they take the derivative. Okay, so this is our function, sine x squared. So the derivative chain rule, inner derivative is 2x, outer derivative is cosine, right? So you get 2x cosine. Oh, it seems to work. Next example. Oh, sine xy times cosine xy. We encountered this function in the plotting part before when we saw like this wavy grid, regular grid out of maxima and minima. Okay, so again we have a function that is to be defined. We can look at the function. Everything is correct or not. And then because it's a multivariate function, I take here the derivative with respect to x and y. So far so good here, right? So this is the function. times, yes, everything still. And then derivative. This is still something you could do with pen and paper, right? Not too bad. Okay. So far, so good. So what you should get until here is like, oh, I can use diff to differentiate all my homework. When you have to differentiate by the derivative, I just need to provide the function and the variables I want to differentiate. Okay, but don't forget the rest of what you learned, because when you get the result, you always can try to simplify. Sometimes Python does it automatically, sometimes it doesn't. You can always try to ask Python again, oh, can you try to simplify it, please? Because there, if you look on top, there's clearly some form of trigonometric relation, right? It's very obvious. Can you see it actually? There are two squares and there's sine cosine mixed term. Do you know how to go from here to here? Maybe something for a break discussion, right? But now you do. You put it in Python, you push simplify. Right? But if you can't do it yourself by hand, then always try to practice again, repeat what you should know. Right? It's a very good training exercise, right? But just not that you like run around or stuff, you use your brain to train. Okay. Then we have the next example where we look into differences between diff and derivative. So differentiate diff, right, provides you with the result of the action of taking a derivative, where derivative itself displays the action to be taken. Okay, so we have here, again, the syntax is just derivative. Note it has a capital letter to start with. Right, and then function, you should take the symbols. What does the function do? It carries out differentiation of the given expression with respect to the symbol. So how does it work? How does it work? I have here a very, very nice function. Look at this. E to the power of cosine x. Did you ever see a trigonometric function in an exponent? Now you see. Do you know how to take the derivative? Chain rule, right? Anyhow, it's much easier when you just use Python. Click a button. So the derivative of cosine is minus sine, and the derivative of e to the power of m is just e to the power of m. So here the derivative is just minus e cosine sine x. Can you do that as well in your head? Yes? Good, very good. Very good. But now we look into the difference between diff, right, for differentiate, and derivative. So when I call simple derivative past the expression and the variable I want to look into, then I get that. Is this the derivative? Kind of, right? But this here is also the derivative. This is the derivative and this is the derivative. What's the difference? What's the difference? In one part of the derivative here is being executed and the other one is not. And so here I still have the operator d over dx being hanging around, waiting to be used. So why would I do this? This is very, very nice when you actually write a discussion about your actions on equations. And then you want to say, oh, you take the derivative. Or what derivative? This one there. What is it before you take the derivative? Or this one there. What is it after you take the derivative? It's that one. So how do you make sure that, for example, you give this part here, right? But at the end, you don't do a copy-paste mistake. Well, you just add to it at the end. And then Python is smart enough, hey, this is the derivative he or she wants to do. And now they ask me to really do it. Yes, that one. So far, so good? Okay, good. So do it evaluates an expression. Right? It really tries to force Python to provide an evaluation. So here, the derivative, the syntax is derivative and do it. Okay, so this we have seen before. Now, so my general impression is that derivatives are easy to take. The difficult part are integrals. Do you know what's actually the difference between integrals and derivatives? Right, so you use derivatives in equations to propagate change in time, predict, for example, the evolution of a system. The integration you do to get a space spanned by a function and come up with just one value. So it's a very different operation. Like you could, for example, integrate the numbers of PCs in that room, right? What we do is actually we go around and count and see where's what, but at the end we just get the number 63. And so we reduce information to a single value. Well, after we put in the boundaries, of course. So how do we do it in SymPy? In SymPy, we have SymPy integrate and SymPy integral to work with, right? No, not this one. So what is going on? Wait a little bit. Yes, a little bit more. Okay. So it's very, very similar to diff and derivative. Integrate performs the integration as good as Python can. Integral just writes you a fancy expression of the integral. We need to provide, again, the functions and the variables. I think in both functions, actually. It's like this. Okay. So here we go with an example already. We have a few symbols, a, b, x, y. We define a function that depends on x and y. Mhm. Let's remind again how to define symbols and functions. Okay, so down here is now the first example, an undefined function. So it's a function which we actually do not know yet in depth. So when I ask Python, hey, what is the integral of f with respect to x, right? It writes me down what is the integral, but does not evaluate it. So wait a little bit. Now, because we never specified what that function f of x and y is, when I ask Python to really do the integration with integrate, right, Python doesn't know what to do. Because why does nobody tell me that the funny thing is here? No, you're all okay with that the whole time. Okay. Okay. So Python doesn't know what is f of x, right? So it's like I do what I can, but I stop here because you need to tell me more if you really want me to do the integration. We can extend the syntax by giving a tuple as the second argument. Here we have a variable and then integration boundary start and integration boundary stop. When we execute this, right, integrate the function and then a tuple defining the variable, start with the integral boundary and stop with the integral boundary. We get an expression like this, and you find again a, b with the function and which variable you actually want to integrate it with. Again, it's the same as with integral because we have never specified what now f of x is. So in the second example, we actually provide a function here, sine of x. And if we do integrate f of x, yes, we do get we need to execute. So now I should be smart enough to tell me that the derivative of sine is cosine. Yes, that didn't work right. Let me try again, execute this, and then execute that. Then we can work with the integral boundaries, here given again as a tuple, x, and then boundaries a and b. Right, and if you have the result minus cosine x, you plug in the boundary from a to b, you get minus cosine b plus cosine a. Yes, looks right. Okay, so now the difference to the function integral is that integral does not evaluate a method, right? It just prints me pretty integral. If we really want to make it evaluated, we again can work with the do it method. So then remember the integral method writes down the symbolic expression of that integral, where its integrate is evaluating the expression as much as possible. So far, so good? So this is an important point because having a little bit help on integrating and differentiating university study in MINT subject could be quite helpful. I suppose you have like, I don't know, you in my education, I needed to take these courses where there was integrals for 6 months straight away. Right? And then there were like square roots of trigonometric functions and this and that. It was always a little bit complicated. Right. But this actually can help a little bit if you face situations like this. Now, more importantly, let's do something more practical, and we talk here about a theoretical probability distribution. Have you seen spherical probability distributions in your life before? And do you know what's a probability distribution? Do you know what's a probability? Do you know what's a distribution? Hmm? Do you know what's spherical? Well, so when I tell you spherical probability distribution, do you know? So normally what you do is you have a spherical, you have a probability distribution in one dimension, right? Like here's the age of people, right? What's the probability of they going to university, right? And then you have a maximum somewhere around 22, right? And then it dies off at 30, right? Some start very early. This is one dimension. This is a distribution, right? Because I have more than one value. It's a continuous function. It's a probability because it represents the chance, right? When I go to on the street and ask somebody, right, I ask your age, and I ask, do you go to university? I get a measure of chance to hit a yes or no through this distribution. Now, a spherical distribution is the same way, just that instead of having age on one axis, I have distance, right? Now, if I go distance, I get a certain probability of hitting a certain value. It depends on am I very far or very near a certain origin. Now, the spherical, because it doesn't depend on direction. Do I go in X? Do I go in Y? Or do I go in Z direction? It just measures how far I go. Okay? And that's all to it. Adjust or you go distance, you can go in X, Y, Z, and it's the same in all directions, just the distance matter. Now, so a simple way of writing down a spherical function is in spherical coordinates. Have you met spherical coordinates in your life before? Yes, you do. And then any function in spherical coordinates can basically be written in a product ansatz, in a radial part, and an angular part. So when the direction doesn't matter, the spherical distribution only depends on distance. But I can incorporate a so-called angular part that says, oh, we cannot go into that direction, but we can go in X and Y direction, right? Okay, and to make things even more interesting, people started to discover, yes, there are certain relations where these functions can be orthogonal to each other, and they work with certain values of indices L, M, and N. So far, so good. Now you don't need to know the details for now. You only need to know there is something like this. Okay. And then people said it's a probability distribution, but we have a complex part in this function. So to get the meaning of probability back, we need to get rid of the complex part. What do? We've introduced a normalization that depends on the absolute square of the function. So here we have an absolute square given by the complex conjugate multiplied by the function, right? And then we take this complex conjugate and say, well, if we have a probability distribution, that function must integrate 2. So far, so good? Okay. And what we do next is we look up what kind of functions are y and r. Are they normalized? We need to integrate, so we dump it into Python. Okay? That's what we do. So the only task we have to do is understand what's asked for, check normalization, find the ingredients, translate them to Python, and push a button. Right, so this is easy. That is something you can do in 10th grade in high school. Right? I have seen that in Singapore. Okay? It's like 10th grader doing this, no problem. Because it's really just like plug in, push a button. Okay, so here are two ingredients, I tell you. Right? One is 1/2 square root 3 over pi cosine an angle. And the radial part is distance times exponent minus r divided by a few factors and then bracket in a second. You can fix the bracket, no problem. Okay, so now we just need to put these things in, and well, I need to tell you A0 is constant, that is fine. Pi is a constant, right? The only variable we have is angle and the distance. Verify. How do we know if this function is normalized or not? We compute the integral given above. So note that the integration of the angle here is between 0 to pi, and the other angle is from 0 to 2 pi. This is the azimuthal angle. This one is the polar angle. When we work with spherical coordinates, we also need to do the transformation of the volume element, dx, dy, dz. To r squared sine theta dr d theta d phi. So far, so good? You get this, by the way, if you take the matrix form of the unit vectors and take the determinant of that. Okay, so here this prefactor. Okay, so our volume integral dr becomes this, and then we just need to copy paste these functions and integrate them. Easy, right? So what do? We define symbols r theta phi r0 through SymPy symbols r theta phi r0, and they are real numbers, right? And then we can go and look at phi and theta because I always mix them up. So here we have phi and theta now, right? And then we define there's a function of y that depends on y and theta. I want to introduce here also now the complex conjugate in SymPy. We get this through the joint function. Here the example is 1 plus I, right? Complex conjugate should be 1 minus I, and with adjoint we actually get that. So because the integrals can be separated from a product, the variables in y and r are separated. I can also separate the integral. So what I do here first is I look into the integral over the angular part, right? That would be sine phi. I said, no, I said wrongly. Phi theta, d theta, d phi. I just need to take my function y and then the function y complex conjugate. How do I get this? SymPy adjoint my function times my function times SymPy sine theta. Remember, sine theta comes from the change of volume element to spherical coordinates. Yes? Don't forget your terms. And then I integrate two values, theta from 0 to pi and phi from 0 to 2 pi. And that is just my SymPy integral. I do this because, well, it's a little bit more complicated than just f of x, right? With integral, I can check if I entered my integral correctly. And after this, right, I could actually say, SymPy integrate. Where is, that is f. Did I define my f already? Here's my f. So the thing is, I haven't defined that y is my function of sine, right? So over here, where is it? Something else was in memory, and I should see actually the same between integral and integrate. I do this, right, to have a lot of checks in my work. So every time I check and I check and I check. Because we're just humans and well, sometimes mistakes happen, but it's our task to avoid mistakes as much as possible. Okay, so what do we do here? Oh, it's break time, exactly. So after the break, we finalize this integral, okay? Good.